Okay, so for today's lecture, we're going to start with section 3.2. And this is on what's called Rolle's theorem. And the mean value theorem. Okay, so these theorems are fundamental theorems in calculus, and they might seem rather theoretical or technical, but these theorems are the reason why we can use something like gradient descent and go in the direction of descent when we're trying to optimize functions. So it's important that you know about them and see the proof at least once for these things, right? So we'll start with Rolle's theorem. Okay. So this theorem states that if f is a continuous function on the closed interval AB, okay, and is differentiable on the open interval AB, with f of A equal to f of B, then there is some number C, which is contained in the interval AB. So I haven't used that notation much before, but that's an epsilon. So all this is saying is C is an element of that interval. So C is some number in that interval. Okay, so and there is some C in that interval such that f prime at C is equal to 0. Okay, so there's a lot of words going on here, so let's just kind of break it down. So f is continuous on that interval, differentiable on that interval, and we're assuming that f of A equals f of B. In that case, there must be a C so that f prime of C is equal to 0 in that interval. So why would that make sense? Well, just imagine you have some closed interval AB, okay, and assume that maybe like say D is equal to f of A, which is also equal to f of B. So evaluate the function at the endpoints, and it's the same. And the function is continuous on the closed interval AB and also differentiable on the open interval AB. So no matter what you do, like if it's continuous and the function is connecting these two endpoints, for some value in there, maybe C, the derivative is going to be equal to 0. That's what Rolle's theorem is saying. Right now, another option maybe would be, so here's AB. So it could be the case that so D is equal to f of A, equal to f of B, D. The function could just be constant, well, then obviously the derivative everywhere in there is going to be equal to 0. Here, this function gets larger, right, than the endpoint. So we know that it's continuous and differentiable in that interval. So we know that it attains a maximum, and that maximum is a critical point. So the derivative at that point is going to be equal to 0, or a critical number. Or likewise, if we went below, then there'd be a minimum, and that minimum would be a critical number, that's C, and then we know that the derivative, if it exists at a critical number C, the derivative is equal to 0. So that's where this statement comes from. Okay, so now let's look at, let's prove it. Okay, so as I did in these pictures, let's just say for notational simplicity that D is equal to f of A, which is equal to f of B. And that's a part of the assumption here that the endpoint's equal. So let's just say let D equal f of A, which is equal to f of B. Just to make life easier, so we don't have to write that and that over and over again. So we have these two cases where, well, three cases really, right? So here's A, here's B, and here's D. The function could go like that, or maybe it goes like that. So we have this picture, and this picture to kind of deal with. The easiest one is this: when the function is constant, the derivative is equal to 0 everywhere, and we get that this must hold. So let's do that case first. So case 1, say, suppose f of x is equal to D for all x that are in that interval. Okay, that's this picture. So then the function f is constant on that interval. So then f of x is constant on AB. And so f prime of x is equal to 0 for all x in that interval. And you can see that the slope of the tangent line at any point is just 0 for anything that's constant. So that means that we've satisfied the conclusion here. There is at least one number in the open interval AB that the derivative equal to 0. In this special case, it happens to be 0 everywhere. Okay, so next let's consider this case here. Suppose that the function gets larger than D at some point, right? Like it's somewhere bigger, right? So suppose f of x is greater than D for some x that's in that open interval AB. So in this case, like all of the numbers are greater than D. All of the images under F are greater than D in that interval. But let's just suppose it happens once, okay? So since F is continuous on the closed interval AB, if you recall, the extreme value theorem says the continuous functions on closed intervals obtain a maximum and minimum on that interval. So we know that f has a maximum on the closed interval AB, say at x equals to c. So there is some maximum over here, and we're going to say that maybe it's at c. Okay, just in. Now, further note, or maybe say note, f of c is greater than d, since, well, we know that for some value of x in that interval, it's bigger than d. So if you're going to have a maximum in that interval, it has to be bigger than d as well. So I can say since f of x is greater than d for at least 1x in that interval. So we know the maximum is going to be greater than or equal to f at that x. Okay. So what we know is there's a maximum in that interval. So so what we can say now is maybe then c comma f of c is a local extrema okay, which implies c is a critical number for f. Right, so if you have a local extrema, which this would be a local extrema right there, then we know that's a critical number. Okay, critical numbers are where we proved in a previous lecture that if we have a local extrema, then it's a critical number, right? Now, a critical number is defined as a value for x where the derivative at that value is either 0 or it doesn't exist. But we know that the function f is differentiable on that interval AB. So we can say that since f is differentiable, do I want to say that? Yeah. On AB, we know that f prime at c exists and is equal to 0. So again, the idea is that it's continuous on AB, it's differentiable on the open interval AB. So the extreme value theorem says that it attains a maximum on that interval. That maximum is greater than the endpoints, because that's what we're supposing in this case. And then that gives us a critical number of the function. And then since it's since it's differentiable, we know that the derivative at that critical number is 0. So for the last case, case 3, suppose f of x is less than d for some x in this interval, and use a similar argument. as given in case 2. And once you do that, that'll complete the proof of Rolle's theorem, which hopefully by case 2 you see is really dependent on this extreme value theorem, together with the fact that local extrema, both max and min, imply that you have your added critical number for these continuous and differentiable continuous functions. And critical numbers are values where the derivative doesn't exist at that number or is equal to 0. Since the derivative exists everywhere in this open interval under this assumption, we know the derivative at that critical number is 0, which guarantees us this. Okay. And again, going back to the picture, I think that the pictures really help. Just again, just to reiterate, here's A, here's B, here's f of A, which is equal to f of B. And it's continuous, so no matter what it's doing, it's going to have so at least one value in there with the derivative is equal to 0. Right, under this assumption. Okay, so that's the statement of Rolle's theorem. So make sure that you have at least the statement written on a piece of paper, because we're going to use Rolle's theorem in a minute to prove the mean value theorem. Okay, so how can we use Rolle's theorem? Maybe suppose, yeah, let's look at this example here. We show f of x equals 2x squared minus 2x plus 2 as f prime of x equals 0 for at least 1 x. Now, we could do this by taking the derivative and then solving for x and seeing what we get. We could also draw the function and kind of get a sense of if this is true. Or we can use Rolle's theorem just to show that we know that there is at least 1x in there somewhere without explicitly having to find it. So okay. Now this is a parabola, right? It's a quadratic, it's a parabola. And I'm going to first see that, oh, this is going to have 2 x-intercepts. And, well, let me find those x-intercepts first. So I'm going to set the function equal to 0 and find those x-intercepts. So does this factor? What does this factor to? So x minus 1 times x minus 2, right? So the x-intercepts for this function equal positive 1 and positive 2. Okay. Now, what does that mean? It means that like on this interval 1, 2, f at 1 is equal to f at 2, right? So that what that says is that f of 1 is equal to f of 2. And the value of the function is 0 in both of those instances, right? So then we can just say, since f is continuous, on this closed interval, and it's a polynomial, which we know that polynomials are always differentiable. Rolle's theorem implies that somewhere in between there, the derivative of that function is 0. I'm running out of room, but I would say Rolle's theorem implies the existence of some c in between there, where the derivative at c is equal to 0. So, I just ran out of room. Okay, so we didn't explicitly find the c, but we know f of 1 is equal to f of 2. We know that it's continuous on that interval, it's a polynomial. We know that it's differentiable on that interval, it's a polynomial. So there is at least one c in that interval where the derivative is equal to 0. So this is just using Rolle's theorem to infer that we have some critical number in there, right? Okay. And we also found the interval where it must exist. Not only did we get that the derivative of this function is equal to 0 for at least one x, we know that there's going to be one inside this interval. So that can be really useful when you're trying to find these local minimum and local maximum. Finding the intervals where you know that it exists helps you narrow down your choices. And if you think about this in terms of gradient descent, instead of making a wild guess as to where the minimum value might exist, you can narrow down what interval you can choose to start gradient descent to speed up your algorithm, to find that local min faster. Here. Okay. Now to the mean value theorem. Okay. So this states that if f is continuous on the closed interval AB, and differentiable on the open interval AB, then there exists some C that's in the open interval AB, so that f prime at C is equal to the slope between the endpoints of the function. So f of B minus f of A all over B minus AX. Okay. So here, I'm going to put a picture on this side so that we can kind of walk along the proof. So imagine we have some continuous function on a closed interval that's differentiable on that open interval. This is like f of a, so right there. And let's suppose like here this is f of b. And we know it's continuous. There's no like breaks in the graph of the function between those 2 points. We know it's differentiable, so we know that there's no spikes. It's more or less smooth between here. Okay. Now, what is f of a minus f of b minus f of a over b minus a? That's the slope of the secant line. So this line here has slope equals to f of b minus f of a all over b minus a. So that's what the right-hand side of this equation is. Okay. Now what this is saying is that somewhere in that interval, there's a c where the derivative at c is equal to the slope of this line, this secant line. So the yellow line is the secant line. So slope of secant line passing through a f of a b f of b. So that's that yellow line is the secant line passing through these points, and that's the slope of that yellow line. So now, just looking at this picture here, I see that it looks like maybe right there, it looks like those are the same slope, roughly, right? So then here, that would be your C, and we'd see that with this picture here, the derivative at C, which is the slope of that line, is equal to the slope of the secant line passing between these 2 points. So hopefully, the statement of the theorem makes sense because it's continuous and because it's differentiable in the open interval AB. It must be the case that this is going to happen, and we're going to prove that here in a moment. Okay. So by the way, what we have 2 points there. We have the slope of the secant line between those 2 points. We should be able to write the equation of the line describing this here, right? So what's the equation of the line? It's like y minus y1 is equal to m times x minus x1, right? That's the equation of the line. So if we just pick one of these points, it won't matter which one. Which ones did I pick? Let's say A, I guess. So I just place that by f of A. And then the slope is f of B minus f of A all over B minus A times x minus A. So I just picked that point to plug in there. So then I see that y, the secant line between this yellow line here, maybe I'll use yellow. I see that y is equal to f of b minus f of a all over b minus a times x minus a plus f of a. So that's the equation of that line. And we're going to use that in the proof. There's a reason why I wanted to write this down. Okay. So the next thing I'm going to do that seems somewhat arbitrary right now, but it will make sense, is to define. So look at our function and how it differs from that line on that interval, right? So for example, here, there's the secant line, or maybe like here, there's the value of the secant line, and then the value of the function is up there, right? So we're going to look at the difference between the secant line and the function f. We're going to just look at the difference, and then we're going to use Rolle's theorem to show that this is true. And you'll see how it works out in a moment. So let's just go ahead and do that. So I'll say notice y equals to f of b minus f of a all over b minus a times x minus a plus f of a is the equation of the secant line passing through these points. So a comma f of a and b comma f of b. Okay. Hopefully, all of you agree that with that. I derived it right here, right? So that's the equation of the yellow line there. Okay. Next, let g of x equal to f of x minus y. So what that is doing is measuring how far away f is from y. Sort of. It's not doing, if we were doing actual distance, we would like square it or something like that. But in a sense, this just tells us how much we're like differing, either positive or negative, from the function, right? So here's the secant line. So notice right here, g of a is equal to 0, right? If you look at the function's value and then you subtract off the secant line's value at that point, there's no distance, they're just like on there, right? But then also here, g of b is equal to 0 because there's no distance between the secant line and the function f. There's also here, whatever that number is, g is equal to 0. If it's like, I don't know, like q or something, g of q is equal to 0 because there's no distance between the function and the secant line. But over here, there is some distance. There's some distance, some distance, some distance, some distance. So 0, some distance. Hopefully that makes sense. Okay. So how can we use this to prove the existence of some value c so that the derivative of f is equal to that slope? Well, we're going to make a few observations about this function g. So note that since f is continuous, on the closed interval AB and differentiable on the open interval AB, the same holds for G. Right, so G is just f plus some linear function, right? So we have linear functions are continuous and differentiable everywhere. That's continuous and differentiable in the open interval AB. So taking that and subtracting off that, that means that this is also satisfying the properties of that and that. So G is also continuous on the closed interval AB and differentiable on the open interval AB. Okay. So moreover, maybe since G of A is equal to 0, which is equal to G of B, can you guess what we can use? We have G is continuous on closed interval AB, it's differentiable on the open interval AB, and the endpoints of G equal. So we can use Rolle's theorem. So we have Rolle's theorem implies there is some C that's in AB so that G prime at C is equal to 0. So somewhere in that interval, G must have a C that has the derivative equal to 0. By the way, if I was plotting G, this would be where G of A is there, G of B is there. The picture kind of maybe looks confusing, but the actual points are so that's G of A, that's G of B, 0. Okay, so now we just have to solve for what that looks like, right? So that's G. So G of X is equal to F of X minus Y. That's Y. So we have F of X minus this line. So X minus A plus F of A. Okay. So that's just a constant, that's a constant, and we have X times a constant, right? So then if we take G prime of X, it's equal to the derivative of F with respect to X minus this times X, and then that's a constant goes to 0, that's a constant goes to 0. So we're just left with that piece right there. That time, so that's like the coefficient of X to the power of 1, so that's what we're left with. So that's what the derivative looks like. So then we know G prime at C is equal to 0 by Rolle's theorem. We know that there is some C that does that. So we just plug in. So 0 is equal to G prime at C, which is the same thing as F prime at C minus F of B minus F of A. Oh, that should have been a subtraction right here, but it doesn't matter. It still went to 0. Like that. So then we have 0 is equal to that minus that, which if you solve for F prime of C, you get that F prime of C is equal, add this on both sides, F of B minus F of A, all over B minus A. We're done. So that's why we use this G function, just this measure distance from the secant line to the function, which happens to be at the endpoints. Since it's continuous and differentiable, it's going to be equal. We can use Rolle's theorem to show that that function G that we made has a derivative at some point equal to 0. We evaluate that and we see that, oh, that means that F prime at C minus this is equal to 0. Solve for F prime at C, and we have satisfied that right there. Okay. Okay, so it's still section 3.2. So let's say from this section, homework, and then okay, and this will, I'm actually going to have you turn this in as well, along with the other homework that some of you already turned in. This will be due, what's today's date? The 22nd. So we'll have this due next Monday. Okay, so that will wrap up this portion of the lecture. I'm going to stop the recording.